Okay, so hopefully everybody can hear me fine, and that. So we're gonna get started with some similar triangles. So with this, I kind of combined a couple sections together because the real key here is just to understand how to quickly identify similar triangles, and then understand that the idea here is that as we scale them up or down, as long as they're similar triangles, then the sides will matching sides will always be proportional. Um, so here I got a couple triangles to show you. So I got a couple triangles here. I got two sides marked off, and so or two angles marked off. Sorry. So you only need to know that two angles are the same to know they're similar. So if you have two angles in any triangle that match, then they're similar, and that's because the third angle is going to have to be the same because this and this, so this dot and this x, when you add those up, they have to the remainder is got to add up to 180. So that's the same in both cases. Thus, all three angles are the same. So whenever you have two angles, you know you have a situation with similar triangles. As well, you need to know only three sides of the triangle to ensure that they're similar. So you got to know all three sides. You can't just have two sides because you could have two sides the same length. I could take these same two sides, but I can bend them in a little bit so that as they pinch in, this longest side here would be shortened. So you need to know all three sides, or you need to know the two angles when you're dealing with the similar triangles. Now, what's nice about similar triangles is we can make use of them, especially useful in real life situations, real world situations, is the right triangle. And that is because when we're working with similar triangles, we can make smaller versions of a triangle to solve problems, to find things like height or distances using them. So the reason why is because if I have these triangles here, and say this is side A, and this is B, and this is C. And to note, when you're labeling triangles, the sides and their angles have to be opposite each other. So this side does not touch angle A. And that's what we mean by like opposite, is that they're not touching each other. So this side B here is not touching angle B. And we label B as a capital for an angle, lowercase as a side, and then our C's again not touching. So in this case here we got a triangle ABC. Often we write it like that. And over here we got triangle, and we'll call this one DEF. And so we got triangle DEF, but to write a similarity between them, triangle ABC is similar to triangle, well, A matches up with D. They're in the same spot, the same angle. Okay, but now it's not BC matching up with EF, it's F matching up with B, so it's DFE. So triangle ABC and DFE are the ones that are similar, and we read them that way so that we know which angle matches up with which angle. Just some naming conventions. We're not getting deep into this portion of trigonometry. We're going to focus more on the sine, cosine, and tangent ratios, and the sine law and cosine law. However, this just kind of leads up into some good useful information regarding triangles. Now, as for some actual work with them, in the textbook there, I believe it was in the first section, 7.1, I had assigned question number 8. So switch over to that and take a look at that. So this is right here. So we're naming a pair of similar triangles in each diagram and explaining why they are similar. So again, they're telling us that they're similar triangles, but we want to make sure that we're labeling them correctly in the right order. So when we're doing something like 8a, we do want to ensure that we label them in the same way. So in this case here, we're working with sides, and we want to ensure that they're similar. So if we take a look at the side AB and we compare that to DE, we can see that it's scaled up by a factor of 3. So it's scaled up by a factor of 3, or AB is 1/3 of DE. So now we can just use that as a guide to see if the other sides match that same scale. And we have to then compare AC to, we can do BC, and, or sorry, AC to, not BC, we're going to the other triangle. AC to DF, and then we can do and I'm writing these out right now, and then I'll switch over that in a second here. So just give me a moment. And then the last pair would be this CB or BC, it doesn't matter, as long as we're labeling the other one the same way, the FE. And so that is 2.5 to 7.5. Okay, so if I switch that back over, take a look at those. So AB to DE is 3 to 9, which simplifies down to 1/3. AC to DF is 1.8 to 5.4, which again simplifies down to 1/3. And CB to FE is 2.5 to 7.5, which again simplifies down to 1/3. So all three sides are scaled the exact same. When we go from the larger triangle to the smaller triangle, we decrease each of those sides by to 1/3 of its original. And thus, because that same scale factor is there, you have similar triangles. So they're all scalable. You could either say it goes this way and down to 1/3, or you multiply the smaller ABC triangle to get up to the DEF triangle. So in this case, you'd have triangle, and I'll switch back here for a second. So you got triangle ABC is similar to, and now A and D are in the same position. They're between these matching sides here and this matching side here. So AD and then BE and then C and F are matching up. So it is just triangle ABC is similar to triangle DEF. So you can use the same idea in the other ones. If we take a look at C, similar to B, you have now the sides touching and they're sharing one side. And in this case here, what we have is these right triangles, and so the hypotenuse is the side that matches up here. So you'd take this little triangle and you could kind of take this J point, and if we pivot on the M, K would come up to J and J would come down to match up with L. So the similar triangles in this case, well, in the little triangle, K is at the peak here and J. So triangle K, we'll call it KJM, is going to be similar to, and now again, K matches up with J in the big triangle, J matches up with L in the big triangle, and then the M, the right angle there is consistent. So if I was writing that out, then what I get is triangle J, or KJM is similar to JLM. Okay, so we're going to find those angles that are going to be equivalent to each other, that match up, and those angles go in the same spots in the naming convention of the triangle. And then again, we could check why they're similar by just taking a look at the matching pairs of sides. So the 6.7 to the 13.4, in that case we're multiplying that by 2, and then we have 3 here, and then we could use Pythagorean theorem and find the height of this side here, and you should get 6. And then the side here 3 should again match up with that height of 6 when we double it, and that 6 doubles to get the 12 here. Thus all the sides would be in a scale factor of 2. So you're going to have to use some Pythagorean theorem as well. Remember, a squared plus b squared equals c squared, or in my case I like to use h squared for the hypotenuse, though we don't forget which position to put it in, but that would figure out that one. Okay, so that's that first bit there. Now what I'd want to do is take a look at the next section, because I find those questions are a little more useful, especially when we get to the word problems. So we had, what was it here? Question number 7, 9, 10, and 11. So in question number 7, and what we're doing is looking for that missing side. So we're going to use that idea of those scaled up sides in similar triangles. So let's do 7b as one, just to check it out here. So in the case of 7b, we have the big triangle ABC, and then we have the little triangle there, and looking in that we have these parallel lines BC and DE, that this setup here would make the ADE angle, so this angle here up on the top part. I don't have a good pointer here. I wish my arrow would stay. But the angle there, ADE, would be the same as ABC. So we have triangle ADE being the same as triangle ABC. And so now we can use these sides and compare the ones we do have to figure out the missing length. So if we do that, again we have ABC similar to ADE, just to note that. And so I can use these as references to match up the pairs of sides. So I had side AB compares to, because you got AB here, so it'll match up with AD, side AD, and that should equal the other sides that we have information on are DE and BC. So we have BC from the big triangle and then DE from the little triangle. So there's all the matching sides, and they should be in the same equivalency, the same ratio each time if they're similar triangles, which they are. So we have our side AB, which is 6 plus x, and then our side AD is just 6, and then our side BC is 10, and our side DE is 4. So what I like to do is just take this guy here and divide that out instead of doing the cross multiplying where I got to move things additionally. So I got 10 divided by 4 first, and that's going to give me my 2.5. And then I'm going to take this 6 and move it over on the next step. So 2.5 times 6. So there's my cross multiplying with the 6. And so I got 2.5 times 6, and that is going to give me a 15. And then x equals 15 minus 6, or x equals 9. So there is my missing value in that triangle. So that missing value of x is 9. That whole side AB would be 9, or would be 15, and then the actual missing portion from D to B. So this missing portion here from D to B would be the 9. Alright, now when we get into word problems, again, a little more kind of situations that might be useful in the real world. Didn't want to switch that yet. So in my case, this question here, to measure the height of a tree, Cynthia has her little brother BR stand so that the tip of the shadow, his shadow coincides with the tip of the tree shadow. So we're just making some similar so what she's done is made some similar triangles here. I've seen this used. Actually, it was the most interesting time I've seen this concept used is in a movie where they cut down a pole and tried to stand at the edge of that pole so that it wouldn't land on them. They did use some triangulation like this to do similar triangles to do that, and not recommended. And I won't give you the name of that movie to discourage you from doing anything silly, but this idea of where, like, trying to shimmy up a tree and get to the top, I'm looking out my window right now and I can see a bunch of trees that if I was to get to the top of them, they're going to definitely bend and break before I even get close, and I'll probably fall out before I get too high up. So to more easily measure them, if we take the idea that the angle of the sun is going to be the same hitting both the tree and BR here, my little brother, we can get the idea that this will be a similar triangle. And they don't have to be standing together. They could be standing separate from each other. In general, the shadow, if you're within a few feet, it's insignificant of how much the shadow is going to change. But if you measure the tree shadow compared to the boy's shadow, then you'll have this nice situation where you can easily calculate the height of the tree. So in that case, all we're doing is setting up some matching ratios. So we got the tree height. Oh, sorry, not T over E. TE, the tree height, TE over the brother's height, BR, should be equal to the respective shadows. So the shadow of the tree would be EC, and the shadow of the brother would be RC. And again, that's just going here and looking that we have our TE should compare to BR, and then our EC all the way across should match up with the RC of the boy. And so now we can fill in those values. So we know we're looking for the tree's height. I'll call that X. The brother's height was given as 1.2 meters. And then the shadow of the tree was measured at 6.5 meters. And then the boy was 4.2 meters in shadow length. And we don't necessarily need the m's, we can cancel those out. So there's our little ratio. All we got to do in each case, 6.5 divided by 4.2. Again, and I'll get like 1.5476. I like using 4 decimal places because as we work further in this unit, we will need to use those 4 decimal places more frequently. And then I just move that 1.2 up to the other side, and so I multiply that by 1.2, and I get 1.8. Where am I here? 1.86. So in this situation here, it looks like we have a tree that is 1.86 meters tall. So it actually is a pretty short tree in this situation here, and she may have actually been able to go climb up there and measure that herself, but we get lazy, right? So the next case here that we're looking at is number 10. And so number 10 has us looking at the width of a canyon. So again, something might not be easy to measure is this entire distance across, because you might not be able to jump across the canyon. But if you can make a similar triangle on the ground near the canyon, what they've done here in this case is measure out a distance of 160 meters, and then you can measure out a point and match up these points using some surveying, various surveying tools. So someone who is surveying this, maybe to prepare for a bridge, would have someone stand on the other side and sight the distance, or use sighting tools and that to get some of these measurements, and then they can calculate the distance across. So we have our two sides here. We know they're right triangles, so they're going to be similar, and they got an opposite angle here to get the other angle that matches. So we can use this again, same type of situation here. So the height of this triangle, and again this little one here, well, it's flipped. The height is the 15. It will match up with the width. So our width to the 15 should be the same as the 160 to the 22 side here. And so if I have my ratio set up here, there's my ratios all set up. And again, it's pretty straightforward. 160 divided by 22, and then we multiply, so that's going to be 7.2727. We're going to multiply that by 15, and that gives us a W of 109. So it's 109 meters across that canyon. It might be difficult to measure independently, but again, using this setup with the ratios, it's pretty straightforward. Last one, number 11, same idea. We're measuring across a river in this case. The same idea could be used measuring across like traffic. They're measuring the distance across a busy road, things like that. You might make use of this. But the surveyors are measuring the width of a river to the nearest meter, and we have the same kind of setup on our triangles, two right triangles. We have this opposite angle here, so they're similar triangles. The 17 and the 50 are the matching sides. And again, why are they matching? Well, if you were to spin these triangles around and get all the angles lined up in the same positions, the 17 and the 50 would match up, and then the 15 and the length or distance across the river, the width of the river, would be the same. So the width compared to 15 is going to be equal to, in this case, 17, or sorry, the width, the river longer triangle to the smaller triangles, so 50 to 70. So it's a similar type of situation to the previous, and again the width is just 50 divided by 17, which is going to be about 2.9412 multiplied by 15, and so that's going to give us a width of 44.12 meters. So when we're working with these triangles, again, it's just a matter of finding those matching sides. And in most cases, you'll be working with right triangles for a lot of your calculations. Some of the earlier examples use a mix mash of triangles if you look back at some of the questions I didn't assign. However, in most cases, when you're actually applying this type of stuff to the real world, what you'll be looking at is the right angle triangle, because we can set up right angle triangles easily in real world situations. Measuring the height of something from the ground straight up and then along the distance along the ground are easy to measure. We usually don't even have to measure the hypotenuse portion, and we'll generally, in real world types of questions, and you'll see this later in the unit when we do right triangle stuff, that it'll be a lot of comparing the distance along the ground and the height, not necessarily the hypotenuse of the triangle as much, even though there is a lot of case for doing that, especially understanding that when we get to non-right triangles. So that is about everything. I believe that's all the questions from this section. Because we have only a few weeks left here, 3 more Mondays after today, really, and I want to make sure we cover everything before the end for those of you working on the culminating. The next topic will be on the trig ratios, and I will probably incorporate solving problems with those trig ratios into the same thing. So 3 and 4, I'll combine those next, and then we'll break up a little bit on the non-right triangles. But those trig ratios, will kind of combine that and the solving problems in the next live stream. Again, if you have questions, send me them on Edsby, send me them on via email. You can send questions beforehand or at any time, and I can try and answer them. And then we'll hopefully see you guys next week.